We start. So I start with the mean curvature flow. Okay. So let's say it's like not a motivation of the mean curvature flow, but let it be a motivation of the talk. Let it be a question you can think about during the talk, and we're gonna answer this question in the middle or at the end of the talk. So if you get lost during the talk, you just remember this question. We would like to answer this question. We would like to discuss this question, which look basic. So we have these following shapes with equal perimeters. These four shapes, they have equal perimeters. The question we ask, which one has the largest area? Okay, we move on. So we're gonna study the change of area to answer the first question. So we start with a curve, a closed embedded curve in R2. So which a curve it doesn't intersect itself, something very nice. And we take a vector field in R2, at which we denote X, and we consider the curve CT, which is equal to C plus TX. So I perturb my curve with in a direction of X in a small time, very small time, so that a resulting curve is still embedded. Okay, we have this volume formula. The change of the area, sorry, the change of the perimeter, we will denote the perimeter with this notation. The change of the perimeter equals to the integral over C of X dot product with H times minus. Okay, so how did we get this formula? Well, there is a way to prove it rigorously, but I'm gonna just show like a sketchy proof of this formula. So if I take something which looks like flat, like a segment, line segment, and I perturb it, so this is the resulting curve in red. If I perturb it, it gives this curve. If I take the difference of the length, the difference is 0. So, and we know the curvature of a line segment is 0. Let's say this is kind of tautological, but because it's kind of definition and a property at the same time. So I take something which is flat, I perturb it, it gives the same length, so the curvature is 0. For those who know the curvature, so who know what the curvature is, so this makes more sense. Okay, so if I take a curve like this, the curvature is pointing in this direction. When we do a change of the curvature, we have this new curve in red or this new curve in red. When I go down, the length decreases. So we see in this formula, if I take X going down, the scalar product is positive. So this is negative and the change is negative. And the same if we go up. If we go up, the scalar product is negative. So the change of area of perimeter is positive. So we increase it. Okay. So now if you don't know what the curvature is, something natural which you leave it in your, maybe not in your daily life, but like regularly, when you are driving at a constant speed, if you are driving directly in a line segment, you don't feel any movement. How to say it? You are going forward. You don't feel movements like transversely in these directions. You are just going forward. But if you are going up a hill and you are doing like zigzags, so you're gonna feel your body going left and right. It depends on how it curves. If it curves this way, you're gonna go this way. If it curves this way, you're gonna go this way. And this is a way of interpreting the curvature in a daily life.
Moxit, may I interrupt you for a moment?
Yeah.
Just for the notations, what is the H1? The measurement?
H1
Yeah.
is the natural measure
Um,
defined on structures of dimension 1. So the Hausdorff measure, let's say.
okay.
So this is a way to measure curves and everything which has dimension 1.
Okay, thanks.
You're welcome. Okay, so now we define the mean curvature flow of closed curves. Okay, so just to see something very, how to say, in dimension, in R2 and for curves, there is only one curvature, which is Gauss curvature or mean curvature or any curvature you define. In a natural curvature is the mean curvature or Gauss curvature. Well, there are like multiples of curvature, but what I mean is like natural curvatures like mean curvature and Gauss curvature coincide in R2 for curves. So a mean curvature flow or a curvature flow, let's say, of curves is a family of embedded curves in R2 which satisfy this relation. So the derivative at any time and at any point is equal to the curvature at time and point. And by convention, we will consider it to be a vector. So the quantity, so the norm of the curvature times the normal, the inward normal. Okay. Here are some examples of mean curvature flows. So if I start with a circle, here's its evolution. Well, the curvature is something which respects symmetries. So if I start with something symmetric, I'm gonna have an evolution which is symmetric. And why do we have this equation? I mean, why does the radius satisfy this equation? Is because when I derive this formula, I get the derivative of r times r equal to -2. So, sorry, 2 derivative of r times r equals to -2. So derivative of r equals 1 over r. And 1 over r is exactly the curvature of a circle. So that's why the evolution is given by this law. Here is another evolution, an evolution of an ellipsoid. It starts like an ellipsoid. It's still like an ellipsoid, but it's looking like a circle with time. Well, the only exact evolution that we know for curves, and we see later for higher dimensions, are the spheres and are the spheres. So because the curvature is somehow complicated to predict at the future for curves that are not symmetric and as nice as a circle. Okay, I'm gonna now show you some other evolutions of curves by the mean curvature flow. Okay, I'm gonna use a website. I'm gonna share. Okay, I'm gonna share my browser. I'm gonna use a website and I'm gonna send the link in the conversation. So this is the website I'm gonna use. Okay. Okay, I'm gonna draw some curves. Do you see the evolution I'm drawing? Okay, here's something looking like a circle. It evolves like a circle. If I draw ellipsoid, it starts looking like a circle, and then it evolves like a circle. Do you see what I'm sharing?
Again, Mouksit, so what is it doing exactly here?
I'm giving examples of evolution by mean curvature flow of some random curves. So let's say this curve like this. This is an evolution of the curve. And now I start with a very, very, very bad curve, but it's starting to look like something very nice with time. And if I let it flow, it's gonna look more and more like a circle, and then it's gonna converge to a point. So you guessed what is coming next. I'm gonna go back to sharing my slides. Okay. Okay, so the evolution is a show of some convex curves that become like a circle, and then sorry, I showed some curves that are very, very, very bad, like not convex, and then they become convex. There is a theorem that states this and proves this by Grayson. So if you start with an embedded closed curve in R2 under the mean curvature, this curve become convex in finite time. Okay, so this is a first property of the mean curvature flow. And why is this true? It's because the mean curvature flow is a flow that homogenizes the curvature. So we start with positive and negative curvatures like distributed on the curve, and the mean curvature flow, it homogenizes the curvature. So at the end, we're gonna converge to a constant curvature, and we're gonna converge to a circle at t equal plus infinity. Anyway, if you start with a circle where the curve has already a homogeneous curvature, so it stays as it is and converges to a point. Okay. So another interesting result is if I start with a convex curve, this curve by the mean curvature flow, it's gonna converge to a round point. We're gonna see an example. We start with a curve which is not convex. So we see that the curvature as this place going outside and here going inside, and this place going outside and here inside. So it's homogenizes the shape and the curvature. So you get something here more homogeneous and now more homogeneous and convex. And after that, at t equals infinity, you converge to a circle. So we are supposed to converge to a round point. So at a point at plus infinity. What is a round point? A round point is well, the meaning of converging to a round point, it means that we are converging to a point, but if we zoom so that the area enclosed is constant, we're going to converge to a circle. So if I start with this shape, this at t equals 0, and I let it move by unfixing the area inside, zooming so that the area inside is fixed, and this is what I've done, I'm going to converge to a circle. Okay. So, and now we have a generalization for manifolds. We start with a curve in a manifold, and we consider its mean curvature flow defined on the manifold. So we consider the curvature of the curve inside the manifold, and we let it flow in the direction of this of the curvature. So we let it flow by this mean curvature flow. So we have the same result. C converges to a closed geodesic in the manifold or to a round point. This is a generalization, actually. of the case of m equal R2, because if m equal R2, the curve cannot converge to a closed geodesic because there is no closed geodesic in R2. So we converge to a round point, and this is the result we stated here. So in R2, if you start with a curve, whatever closed curve, embedded closed curve, if it's convex or not, it's gonna be convex in finite time, and then it's gonna converge to a round point. And in the case of manifolds, it's gonna converge to a round point. Okay, so here's an example. If you take the torus, if you start with this curve, which has this point as an endpoint, so we identify this point with this one because we identified this segment above and this segment below and this segment at the left and this segment at the right. And this is how we construct torus. So these curves that start with this point and it goes back, it circles around and it goes back to the same point, gonna converge to this closed geodesic. These curves, which doesn't make a loop around the torus, gonna converge to this point. So this curve gonna converge to a round point, and this curve is gonna converge to a closed geodesic. Okay. So one application of Grayson theorem on manifolds. One application is the following. If I start with S2 and I put some metric, any metric which is diffeomorphic to the natural metric on S2. So S2 with this metric admits at least one closed geodesic. And how to prove this? We foliate S2 with curves converging to the pole north, to the north pole, and converging from and in below to the south pole, and we let them flow by the mean curvature flow. So the curves that are very close to the North Pole gonna converge to the North Pole. And because they have two choices, either they're gonna converge to a geodesic, the closed geodesic, or to a point. But when you are very, very close, when you have a curve which is very, 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 very small, you can prove that it's gonna converge to a point. And also here, they're gonna converge to a point. And we're gonna look at the limit of all these curves. One of them some of them above they're gonna converge to the North Pole, some of them below they're gonna converge to the South Pole, and by continuity of the flow, we surely have a curve that's gonna converge in the middle, not to the North Pole, not to the South Pole. So it's gonna converge to a closed geodesic in the middle. Okay, so we go back to R2, which is the case that is interesting for us. Another application of the mean curvature flow is the isoperimetric inequality. So how to prove the isoperimetric inequality? Well, actually, I didn't recall isoperimetric inequality. So sorry. First, before we prove the isoperimetric inequality, we start with this. We start with a intermediate result. We define AT to be the area inside CT, the curve, moving the curve at time t. We take the derivative of the area. The derivative of the area is equal to the integral over CT of H dot product with N. N is the inward normal. So how to see this? So you take your curve and you move it in the direction of H, and you take the difference of the area at time t and at time t plus epsilon, and the difference will be like something around the boundary, around the curve, and we divide by epsilon. You can prove easily that the derivative of the area is equal to h epsilon to h times n. And if you know the divergence theorem, this is just the a direct application of the divergence theorem. So by this formula, we know that by this formula, we can go further. We can go further and we use the Gauss-Bonnet theorem. What does Gauss-Bonnet theorem say? It says that the integral of the curvature over a curve is equal to 2 pi. So the derivative of the area is equal to minus 2 pi. So the area is a affine function. It starts at a0 and it disappears at some extinction time. And we can set the equation and prove that the extinction time is equal to a0 over 2 pi. So this gives us a tool to compare between the shapes that we saw at the very beginning. So if I start with these shapes, I just how to compare their area. I apply the mean curvature on them. I apply the mean curvature, and the first one to disappear is the one who has the least area. The last one to disappear is the one who has the biggest area, the largest area. So this is answer these equations. I mean, this property answers our question. We go further on to prove the isoperimetric inequality. So we consider, so the goal is to prove that 4 pi times the area is less than the perimeter to the power 2. And this is the isoperimetric inequality. Sorry, I forgot to pause somewhere. Okay. Okay, so this is the thing we're gonna prove. How to do that? We start with a curve C, and we consider AT the area inside it, and this thing, the length of the curve at time t, and we consider this quantity and we derive it with time. So we take the derivative. The derivative is equal to 4 pi, and the derivative of the area is this quantity. Sorry, this quantity. Well, I cannot select, I cannot highlight it. So this quantity, the integral over ct of h dot product with n, and the derivative of the perimeter is the integral is the perimeter times 2 times the derivative of the perimeter, because here we have square, and it gives this quantity, because when we take the derivative of the perimeter in the direction x, we get the integral of the dot product between h and x. But now our x is h, so you get h squared. And now to conclude, we just put this term here, and we replace 2 pi by the integral of h over ct, and we use Cauchy-Schwarz inequality to prove that this is positive. So this quantity is increasing. This quantity is increasing, and we know that at extinction time, this quantity will disappear, will be 0. So we know that this is bigger than. So we know that at t equals 0, we have this is negative. So 4 pi times the area at time 0 is less than c to the power 2. Okay, so what does this mean? What does the isoperimetric inequality mean? It means that if you fix the length of the curve, so the area inside it, it cannot go to infinity. It's bounded by the length of the curve to the power 2. Or if you fix the area inside the curve, the length of the curve the length of the curve cannot go to 0, so it must be bounded from below by 4 pi a under the square root of 2. Okay, so this brings us to a very famous problem, which is the foundation of Carthage city. So a legend said that there was a king that showed a map to his fellows, and he brought a rope and he put it on the map, and he said, here's this shoreline, and here's this road, and here's this rope. Put it in a way that its endpoints connected the shoreline, and such that the area inside the rope, the area determined by the rope and the shoreline, is as large as possible. So we have all these possibilities. We can put the ropes this way and we build Carthage in this way. We can build Carthage this way. We can build Carthage this way and this way, but none of them is the largest. None of them is the best option. None of them satisfy the largest area, because by the isoperimetric inequality, the shape that satisfies the largest area is a half of circle. And how to understand this is just you take the symmetry with respect to the shoreline, and you have something which is closed, and then if it's it has a largest area, then when you add the symmetry, it still has the largest area, but none of them has the largest area, considering that the rope length is fixed, because the best configuration is satisfied by the circle. Okay. This problem called Carthage problem, and also called Dido problems for those who knows the isoperimetric inequalities problems. Okay. So now we're gonna generalize some of the results and the study to manifolds of higher dimensions. Okay, so the mean curvature is an intrinsic measure of the curvature. So not to confuse with the Gauss curvature, which is this is an extrinsic measure. Not to confuse with the Gaussian curvature, which is an intrinsic measure. So Gaussian curvature is for manifolds that are not necessarily embedded. You consider that just a manifold defined without embedding it. But the mean curvature is you embed the manifold first, and you try to compute its curvature. And when you try to compute its curvature, its extrinsic curvature, you find the mean curvature. It depends on how you embed it. Okay, in another way, it depends on how you embed your manifold in Rn. So for example, a sphere, it may have different mean curvature depending on how you embed it in your space in Rn. Okay, so if I take M a submanifold, a D submanifold of Rn, then the mean curvature is defined as follows. You take the principal curvatures and you multiply them by the direction for which you computed the principal curvature. So you put your manifold and you draw orthogonal lines on the manifolds, and in any direction you compute your principal curvature, you see your manifold as a curve. So you take a direction and you just consider the restriction of your manifold on this direction, so it becomes a curve, and you compute the curvature of the curve, and this is the principal curvature in the direction you've chosen. And you do this for an orthonormal basis of directions, and this gives you the mean curvature at a certain point. So it happens that the mean curvature satisfied a variational equality, which is given by the following formula. So when you take the derivative of a manifold after pushing it by the identity plus t very small times a vector field x, when you take the derivative of the area, So this is the Hausdorff measure of dimension D. When you take the derivative of the area of this manifold, sorry, the area is not what is inside the manifold. So the area of the manifold, not the area enclosed inside the manifold, the area of the manifold, the area of dimension D. So when you take its derivative, well, you apply what we call the area formula, which is basically the change of variable formula. You get this quantity. So what does this come from? Actually, when you take the derivative of volume in a normal situation, you get a divergence. But as the volume of a manifold is computed by taking restriction of the volume to some sections which are tangent planes, like when you compute the Jacobian, which express the volume, you add a projection on the tangent plane TYM, and you compute like a sub-Jacobian. So when you take the divergence, you take a divergence with respect to the tangent plane to get this formula, and then you apply something like it's like a divergence theorem to pass from this expression to this expression. Okay, so I forgot to write lambda e differently. So lambda e, you can write it as a divergence of n. Lambda j is the divergence of nj somehow. So we see here a divergence. You use a divergence theorem to pass the divergence from x to somewhere else, and this somewhere else becomes the mean curvature. Okay, so well, here I gave the divergence with respect to a tangent. So if I take a tangent t, the divergence is, instead of taking the trace of the gradient of x, or let's say differential of x, we take the trace with respect to t, where t is a plane of dimension d. I will come back to this definition later. Okay, sorry, 1 second. Okay. I'm back. So I'll come back to this definition later on. But basically, it's just the planes of dimension d living in Rn. Okay, so what we should recall is that the mean curvature is the sum of the principal curvatures, and also the mean curvature can be obtained in this way. When we take the derivative of the area of the manifold, it gives the mean curvature by this relation. Okay, now we define the mean curvature flow. I forgot to zoom in. Now we define the mean curvature flow. So the mean curvature flow is defined as for from a higher dimensional submanifold is defined as for curves. So we take a family of CK submanifolds. So we take a manifold of CK regularity. So when you can differentiate like K times basically. We take a family of CK embeddings of this manifold into Rn. We say that this is a mean curvature flow if the derivative at any time and at any point is equals to the mean curvature. It's basically the same definitions for curves, but for a higher dimensional structure. So examples of mean curvature flow: we have minimal surfaces. Is when the mean curvature flow the mean curvature flow is static. It doesn't do anything. It leaves the surface static. is when the surface has mean curvature equal to 0. For example, when we take planes or D planes in Rn, they have curvature equal to 0, so they do not move at all. Another examples of mean curvature flow is the mean curvature flow of spheres. So as for circles, we have the same relation, but we have D here. It's because when we take the derivative of R with respect to T, we get 2 times R times the derivative of R equal to 2D. And this comes from, and this gives R prime equal 2D over R. And this is exactly the mean curvature of a sphere. And how to find this is just you take D orthogonal directions, you compute the curvature in the direction of any of these directions, and the curvature is constant, equal to 1 over R, and you take the sum and you get D over R. Okay. So now we discuss another formula of the mean curvature. So the mean curvature is defined first as this way, because the sum of lambda, as I forgot to write this before, is the sum of lambda j and j, and lambda j we can see it as the divergence of nj, and this is for formal computation, but we can make it rigorous. So this is equal to the divergence of the orthogonal an orthogonal frame. We can write it like this. This is the tangent, and we put this in the orthogonal, because here we have normal vectors. And if we write Tm plus Tm orthogonal equals the identity, and we admit that the divergence of the identity equal 0 because the identity doesn't move, so we can obtain this. This is formal, but we can make it rigorous. And the divergence of Tm, we can write it as the Laplacian of the identity of the manifold, because we know that the Laplacian is divergence composed with the gradient. We can understand Tm as the gradient of M, of the identity of M, so we get this formula. Okay, and by this new definition, or I mean other definition of the mean curvature, we can obtain the following result. It's the short time existence of the mean curvature flow. And how do we obtain this? It's from the quasi-parabolic PDE's theory. We know that when you have a parabolic PDE, it's like dt equals Laplacian, dt of u equals Laplacian of u. We have a theory behind this that implies the existence for, I think, for t equals plus infinity, if I still remember, but at least we have existence for a short time. So here we have a parabolic PDE. We have the derivative equal to a Laplacian of identity map of M. So we use the same techniques of parabolic PDEs to prove that any quasi-parabolic PDE has a short-time solution, and we apply it for the mean curvature flow, and we have existence of mean curvature flow for a non-trivial interval of time, for at least a short-time interval. For an for in these two cases, we have existence for any t. Well, here it doesn't change anything, and here it disappears. It disappears in finite time when t equal r2 over 2d, and then it becomes just a point, and then it disappears. Okay, so what should I add here? So we can still, okay, but we know that is a short time existence of the mean curvature flow. So the study we're gonna conduct later on makes sense. As for the curves, if as for the curves, well, this result was not discussed for the curves. Well, what we said for curves is that we start from any curve, convex or not convex, it's going to become convex in finite time, and then it's gonna converge to a round point in R2. Okay, here we take a manifold of dimension d in Rn, and we assume that h is bigger than 0. What does this mean? It means that the sum of the principal curvatures is bigger than 0. So if you have this hypothesis, then our manifold become convex in finite time. And then what we have later on, if M is convex, then M becomes a round point in not necessarily in infinite time. It becomes it becomes a point in finite time if it's a circle, if it's a sphere. Well, sorry. If M is convex, MT converges to a round point. This means when we zoom so that the area inside is constant, we converge to a sphere. But we do not converge to a sphere in a finite time unless we start with a sphere. So we are getting closer and closer to a sphere. Okay, and this is okay. The first result is it's derived from the first result is true because the mean curvature, as it is a quasi-parabolic equation, we have the Laplacian, and the Laplacian does its thing. So the thing it does is that it increases the minimal principal curvature. It increases the minimal principal curvature, and the minimal principal curvature becomes positive, and then the minimal principal curvature becomes positive. So we have only positive curvatures, and we are in the second case when M is convex. M is convex if and only if all the principal curvatures are positive. So now we have the homogenization thing, which is ensured by the Laplacian, because the Laplacian homogenize. The curvatures tends to converge to a constant value, and all of them converge into a constant value in a homogeneous way. They try to get closer to each other's. So that, and this what implies that the mean curvature of a convex manifold converges to a round point. Okay, here's an example. Here's a manifold with mean curvature bigger than 0. It becomes convex. Well, this is not convex. We see exactly because if I take points here and I take points here, if I take the segment linking these 2 points, the segment goes outside the manifold. So the manifold is not convex. But the mean curvature flow homogenizes the curvature and increases the minimal curvature, which is positive, and it makes it which is negative, and it makes it positive. So we get something which is convex, and then we converge to a round point. Here we are going. Here the sphere. Here the manifold is going to look like a sphere with time. If we zoom, we see that it's going to converge to a sphere at t equals plus infinity. Okay, so for those who knows the Ricci flow, which is a flow that homogenizes the curvature as well, but differently, and defined in another context, in the context of submanifold, in the context of manifolds, not necessarily not embedded. So the proof of Huysken that if a manifold is convex, then it's converged to a round point is exactly the proofs of I don't remember his name. Richard Hamilton, that Ricci flows starting from a convex manifold converges to a round point. I don't have the exact details about this, but I just read it during my thesis. Okay. So now we will list one of the most important results about mean curvature flow, which is the avoidance principle. The avoidance principle is a property of the mean curvature flow satisfied in codimensions 1. When we take a hypersurface, it satisfies the principle that I'm listing here. So first, we explicit the formula of the mean curvature of a hypersurface. If I take a parameterization f of the surface of the hypersurface, the mean curvature is given by this formula. So we see that this is like, if I apply the divergence here, I get the Laplacian of f, and then I apply the divergence here, I get an extra term. This what makes the equation quasi-parabolic and not parabolic. And we see that if the gradient is very small, this will look like a Laplacian, and this is the idea behind the avoidance principle that we see here. So the avoidance principle, if I take M and N two hypersurfaces in Rn, if their intersection is empty, then the intersection of their flows is empty as well. So if I take two hypersurfaces, one inside the other, or they're completely disjoint, they're not. It's not one inside of the other, just one in a place and the other in another place, and I let them flow by the mean curvature. Their flows will not intersect if they do not intersect at time equals 0. How to prove this? Basically, we consider two hypersurfaces that are touching each other at a point, and we compute their mean curvature. So the mean curvature of M, which is here below, is equal to the Laplacian of the parameterization at 0. Remember this formula, because the gradient is 0. So we have H equal Laplacian, and the same for G, which is equal to the mean curvature of the manifold N. And we have this inequality. If F is above G, the Laplacian of F is greater than or equal to the Laplacian of G. So these observations allows to prove this principle. So if they intersect, we have the mean curvature of N is bigger than the mean curvature of M. If they do not intersect, we have the mean curvature is strictly bigger, so they will not intersect at any time. This is somehow how to prove this formula, this principle. I'm going to show you some simulations of the avoidance principle of curves. Okay, I'm going to share the same website as before. Okay, so here are some illustrations. I take a curve, I take another curve inside it, and I let it flow. Their mean curvature does not intersect. I take another curve inside, mean curvature does not intersect. Take another inside, mean curvature does not intersect. The mean curvatures avoid each other's. Let's take this, for example. I take another one inside, they do not intersect. Take another one. I can draw curves here. I let them flow. Their flow will not intersect the big curves outside. Okay. So this property allows.
Just a quick question, Moses. So
Yeah.
they reach so they become a point at time infinity, right? So
Yeah.
they're essentially
They all becomes.
so they can touch each other at time infinity. That's what this.
Actually, yeah, they become a point. If I zoom out, if you zoom, sorry. Actually, the point disappear. The conversion to a round point, it means that you're gonna converge to a point, and then the point gonna disappear. I forgot this step. The point will disappear instantly. But if you zoom this point, if you zoom, the curve will not disappear. Will just converge to a circle. Is it clear what I just said?
I'm not sure. Can you please repeat?
Okay, so I take this curve, it disappears.
Yeah.
The flow disappear, becomes a point and then disappear. But if you zoom, if you zoom this flow, the flow will not disappear. I mean, yeah, this looks like a an
Yeah, I mean,
counter.
yeah, this doesn't contradict the theorem. I'm just because the theorem says for any t positive, they do not see each other. That's, but it doesn't say anything about when t goes to infinity. That's what. Yeah, so my question is more or less related to the behavior at t equals to infinity. I'll be more precise maybe later at the end. I have another question, which is maybe.
This is a valid question. This is a valid question. So yeah, let me formulate it this way. I let my curve flow, and at a finite time, it will disappear. At a finite time, it will become a point, and then once it is a point, it disappears.
Okay. Okay.
Now, if I zoom so that it doesn't become a point, I still give it the, how to say, I still give it the freedom to evolve, because the area inside is constant. So I let it evolve and evolve. So it's not going to disappear. It's going to converge to a circle. Yeah. So let's say by definition, the flow of a point is just disappearance, just disappear. A point disappear. So when a curve becomes a point, it disappears. Yeah.
Okay.
Yeah, because yeah, I think with my definitions, it implies that a point is just still becomes a point. Well, I will think about it, but yeah,
Okay.
the question is valid.
No problem. Okay. Thanks.
So this will lead to another, let's say, a bad property about mean curvature, which is the following. Well, first I have to say something. The mean curvature in higher codimensions, does not satisfy the avoidance principle just listed here. And how to see a counterexample can be easily constructed. We just take two inlaced disjoint circles. So I take two circles like this and let them evolve. So the circles in R3 or any dimension, they're gonna evolve as like they were evolving in R2. So we have the law RT square equal R square minus 2 dt. And here this one is gonna evolve like this, the other gonna evolve this way. So they're gonna touch each other. And the avoidance principle is not satisfied. And if you see the proof, in the proof we considered like one inside the other to prove that it's like one in the outside gonna push the one inside. But for curves you cannot say, but for codimensions, higher codimensions, the hypersurfaces may be enlaced, so you cannot tell who is inside who. So it's like a topological constraint. If you can say who is inside who, so you can prove that they can avoid each other, but as they're enlaced, they cannot say how it's gonna, you cannot predict how it's gonna evolve. So one of the bad things about the mean curvature flow is that does not the solution does not exist for every t. For curves, everything goes very well, and for any t we have an evolution of curves. But for higher codimensions, we most likely encounter singularity. So here's an example. We take something which is diffeomorphic to S2. Well, this is in R3, and this is something of dimension 2, but my drawing skills are very bad, so I draw it like this. And here are two spheres. This is a sphere, this is a sphere, and this is a torus. Well, the spheres gonna evolve as we saw before. They just gonna shrink in somehow, and the torus also gonna shrink. The torus gonna shrink to this point. The sphere's gonna become like this, and they're gonna continue to flow. But this thing, which is diffeomorphic to S2, gonna develop a singularity here. Why? Because by the avoidance principle we just stated, the evolutions avoid each other at any time if they avoid each other at time t equals 0. So here we have the spheres and the torus. They don't see this surface. They are disjoint from the surface. So the evolution gonna be disjoint. So this surface gonna try to avoid the evolution of the torus, so it's gonna pinch in this point. So this is how we know that the mean curvature flow does not necessarily have a solution for any t. So this leads us to the next question: how to define mean curvature flow past singularities. We saw that sometimes we encounter singularities, and actually most of the time we encounter singularities. How can we define the mean curvature flow past these singularities? Okay, I finished my first part of the talk.